Example 1.5.3. Assume an AC power system with a load voltage of 110 volts provides power to a city with 200 lamps, each of the lamps having a resistance of 220 ohms. The power plant is located 1 kilometer from the city, and it is connected via 10 gauge solid copper core wire that has a resistance per unit length of 3.28 ohms per kilometer. A step-down transformer at the load is used to reduce the voltage at a ratio of 1000 to 110, which is the transformer ratio, and a step-up transformer is used at the generation site to increase the voltage at a ratio of 110 to 1000. Determine the generator's voltage necessary to supply the load at the supplied voltage, and determine the ratio of the power delivered to the load to the total delivered by the plant. So this example is a comparison of the Edison DC system versus the Tesla AC system. Our givens are best summarized by creating a circuit model. First, you should remember that the AC system uses a AC voltage source. We're going to assume that the numbers given were RMS, and so we've got the source voltage, the RMS voltage that we're trying to calculate. Remember, AC sources are circles instead of the DC source that we used in the previous example. We then connect that voltage source, which represents our AC generator, up to a transformer. The transformer symbol looks like two parallel inductors. This is where the line resistance comes into play, because the line connects the step up and the step down transformer. And then there's a second transformer that serves the load. That load being the parallel connection of those lamps. And we were told what the line voltage was at the load. It's 110 volts AC to get those lamps to light up appropriately. So that is kind of the most basic of the US transmission systems. We would have a step-up transformer, some sort of connecting line, and then a step-down transformer near the load. And for this, just like in example 1.5.2, we're asked to find the source voltage at the generator and the overall system efficiency. So some of the solution we already solved for, so we don't need to repeat ourselves. We know that the load resistance, the parallel effect of all the different lamps is 1.1 ohms, so we can just write that down. That was solved for in 1.5.2. And we know that the line resistance is 1 kilometer of 3.28 ohms per kilometer line, connecting to the load, and then the same connecting back, so our total line resistance is going to be 6.56 ohms. So that is what fills out our circuit model up there. I'm just bringing both those numbers over from example 1.5.3. Oh, I forgot, we also in our circuit model need to identify what the transformer ratios are. So at the load we had a step down transformer, which means it decreases the voltage from 1000 volts down to 110 volts. And at the generator we had a step up transformer, which increases the voltage from 110 to 1000. We're going to start at the load and work backwards in this problem. That's the general solution method for most transformer problems, is to analyze the load and then solve for the voltage source. So to do that, what we need to do is calculate what the current through the load is, and then what we'll do is we'll transfer the voltage and current at the load through the transformer into the distribution system. So I'm going to start by calculating the load current drawn by the lamps, and so I'm just going to isolate that portion of the circuit. I've got my 110 volts across my 1.1 ohm resistor. And that's how I'll determine what the current in that loop is. So simple application of Ohm's law. So the load current there is just going to be 110 volts divided by 1.1 ohms, and that gives us a current of 100 amps. So that's the total current drawn by all those lamps is 100 amps. And now I need to transfer that current and the load voltage through the transformer into the distribution system. Well, before I do that, I do need to calculate efficiency later, so I'm going to go ahead and calculate how much power is absorbed by that load. So there's a couple ways to do this. Power is V squared over R, or I squared R, or I times V. So I'm going to use the I times V method. So 100 amps times 110 volts is 11 kilowatts. So same load consumption as in the previous example. Oh, sorry about that. I've got some artifacts here I need to clean up before we continue. Let me get rid of these here. Okay, so we can get back to it. My apologies. So now what we need to do is transfer that voltage and current from the secondary of the step-down transformer to the primary of the step-down transformer. And the term secondary is just kind of interchangeable with output of the transformer, and primary means the input of the transformer. So for this one, we want to know what the high side of the transformer is. What is the voltage on the high side? So I'll write input, or high would be how you would identify that. Either would be okay. So for the second transformer, the high side voltage is equal to the low side voltage times the turns ratio. Symbol for turns ratio is just TR. So we already know that the low side voltage is 110 volts. That was given in the problem statement as the load voltage. And then we just need to multiply that by the turns ratio, 1000 over 110. So that gives us a high side voltage of transformer 2 of 1000 volts. Now what we need to do is calculate the current flowing through the high side of transformer 2. And we do that using the current flowing through the low side of transformer 2, but instead of multiplying by the turns ratio, we divide by the turns ratio. So we get 110, I'm sorry, not 110, it's 100 amps divided by 1000 over 110. And that's going to give us a current flow in the high side of transformer 2 of 11 amps. So now we know how much voltage and current is flowing through the primary and secondary of transformer 2. The amount of current flowing through the primary of transformer 2 is also going to flow through that line resistance, and so we can calculate the voltage drop across the distribution line if we know the current through it, just from I times R. So that's what we're going to do next, is calculate that the current flowing through that system. And then we'll calculate the voltage drop through our line, and that'll tell us what the voltage at the terminals of T1 are. Okay. So let's do that next. We're going to calculate the line voltage as just, this is the voltage drop across the line. It's the current flowing through that resistance, which was 11 amps, and we're going to multiply that by the line resistance, which was that lumped 6.56 ohms. So we're going to get 72.16 volts is the voltage dropped in the transmission system due to the resistance of the line. So that's the voltage drop across the resistor. We can also calculate the power consumed by heat loss or radiative heat in that resistor, and it's just the voltage times the current, 11 amps times 72.16 volts. It's going to give us 794 watts. Could have got the same answer with 11 squared times 6.56, or 72.16 squared divided by 6.56. So to calculate the voltage at the high side of transformer 1, we're going to use Kirchhoff's voltage law around the distribution system loop, and that is going to be the sum of the high side voltage on transformer 2, so the left side of transformer 2, plus the voltage dropped across the line resistance. So that's 1000 volts plus the 72.16 volt drop across the distribution line. So the output of transformer 1, the high side of transformer 1, has to be 1072.16 volts. That's I'm showing that here. And what happens is it's going to be reduced because this was a step-up transformer and we're working backwards. So the voltage at the source is going to be lower than that by 110 over 1000. So I'm going to calculate the transformer 1 low side voltage, and that's going to be the high side voltage, just times the turns ratio, which was 110 over 1000. So we take 1072.16 volts and multiply by 110 over 1,000, and we get 117.94 volts on the primary side of the step-up transformer, or the low voltage side of the step-up transformer. We can calculate the current flowing through the primary side of the low voltage transformer by dividing by the turns ratio. So we're going to take that current flowing in the secondary, which was 11 amps, and we're going to divide it by 110 over 1,000. And let's see, what do we get there? We should get 100 amps of current flowing there. We can determine the power being sourced by the AC voltage source. We could either add the load resistance, or we could either add the load power and the line power. That would work. But in this case, I want to just show that you can also calculate it from the product of the voltage at the voltage source and the current supplied by the power source. So that was 117.94 volts. What is the generation voltage times 100 amps? Gives you 11.794 kilowatts. So I want to calculate the efficiency of this power system. That is 11 kilowatts divided by 11.794 kilowatts, and that gives us an assistance efficiency of 93.27%.